Well, we already discussed high performance computing and its importance. There is a class of computing which is typically a little on the edge of high performance computing, namely agent based modeling. And so, when we were doing our material science, we had a nice, pretty picture of a new nanomaterial. That uses fundamental Newton's laws or Schrodinger's equation or Dirac's equation, the fundamental equations of matter to describe atoms, electrons, and molecules. You want to not just um, simulate materials, you want to simulate the stock market, the transportation system, or the reaction of population to disease or some unexpected shock like a 9/11 event. Then the basic entities are not subject to Newton's laws. So people do not obey Newton's laws. Their behavior follows eventually from Newton's laws, but you can't make a model of people as bunches of atoms and electrons and molecules and realistically solve that to decide what they're going to do when you have a 9/11 event. Rather, you introduce a new type of science where you um, set up a person as a so-called agent. An agent is a computer entity which receives has a set of rules in it which tell you what it does when certain things happen. And so agent-based modeling is very important. It's been used for many years by the Department of Defense with a technology called HLA or DIS, which is used to do their simulations and use cases 23 and 24 on spreading a disease and reaction of people to scenarios. Those use agent-based modeling, which is a very important technology for the subset of cases where it's relevant. Um, and typically, if you read the simplest books, it will tell you to use a so-called event-driven simulation to evolve agents, but that's the world's most inefficient, slowest thing. It's the most precise and best if that's all you can do, but typically use some heuristic to make it run faster. Okay. Well, we already mentioned fusion, and we actually showed you the example of my picture ending up with a fused bottle at the top right. And there's another magic term here, knowledge management. Data fusion and knowledge management are not very well defined, except it's obvious what the intuitive meaning is clear. We have a huge amount of data, which remember is turned into information and knowledge, and we have that from many different sources, and we need to combine it to get the answer we want. And that's what data fusion and knowledge management are doing. There are many people who work in this field, and it's rather hard to find out exactly what they do. And but I believe that slide, which is mentioned here, the raw data, the decision slide, shows the essential idea. You have a workflow. Workflow is very important, and it's present in nearly a lot of these different use cases we have, where you have multiple services and clouds linked together, typically with data. Where here we're using data in this generic fashion to mean data or information or knowledge flowing from one service to another, getting refined or transformed and filtered as it goes from one to the other and ending up with a better understanding by, or hopefully alternative understandings. The simplest type of fusion actually is to just take a portal, take 6 sources of information about a subject and place them one in each of 6 gadgets, and that's the one form of fusion, but most fusion would be a little more sophisticated than that. When we come to global optimization, where we're summing over giant, we're parameterizing the world, summing over all the information we have. That's effectively a fusion algorithm because it's taking disparate things and adding them together to reach some sort of conclusion. So that's this exascale global optimization ego classification. So let me now come to that. So it's a rather flamboyant title, which was invented in some meeting I was at a few years ago, and it basically points out that there are a class of artificial intelligence problems phrased as giant optimization over many variables. This is what I call global machine learning. And the case that's most familiar is called chi-squared or maximum likelihood formulations, which after you take the log of the maximum likelihood, you always get, and you take the right sign, you always end up minimizing a sum of terms. And those terms are a mix of observational data or derived data and parameters which you wish to determine. And this type of artificial intelligence formulation is pretty different from the rule-based or expert system AI. And it's probably the most appropriate when you really have a lot of information, because you can try to minimize the sum of a billion terms, but you can't really reliably apply a billion rules. They will interfere with each other. Whereas if you sum them up and try to minimize them in the least squares fashion, you can get them to trade off against each other in the most satisfactory fashion. One example we have, a very simple example, is called multidimensional scaling, where if you want to solve the AI problem of mapping entities either in the non-vector space or an arbitrary vector space to 3 dimensions, then you have a global sum over n of them, essentially n squared measures of similarity, and you minimize the weighted sum of the squares of the similarities minus the predicted similarities when you assign them to a vector space. Another good example of ego, in fact, probably the most important, come from information retrieval, where you take the world's documents and try to summarize them or find topics implied by them and so on. I expect ego to grow in importance, and you could say learning networks are also in this area. I didn't really classify anything as security. When we discussed the NIST activity, we noted there was a security and privacy working group. Security is essentially present in all use cases. And the word security covers many, many areas. Authentication, authorization, how you log in and you decide that you use a computer or you access a piece of data. There are lots of privacy issues, either especially in the healthcare area, say because of personal data, or in commercial areas because due to proprietary data. We also have to worry about tampering when you have these pictures of man in the loop or whatever, attacker in the loop, where you have a nice workflow, and unfortunately one of the services has got corrupted and is stealing what the data is coming in and spitting out garbage, which confuses the world. So there are important issues in security with you do cloud computing, because cloud computing is shared computing. And so you can have, so you worry that if you have a proprietary application running, it's telling you which the company will tell you what types of calculations the company is doing, even though there is no trivial way of finding out. Maybe another program running next to that program can see what data sets are being accessed and effectively look at the execution model of that program and extract and effectively compromise the proprietary nature of the computation. So in the end, it points out that the three broad areas: commercial applications, proprietary, defense as incredible national security issues, and health and social studies, and some of those in the network science area have privacy issues from the use of personal information.